So I would like to welcome everybody and our guest, Dr. Hussain, today to the next seminar in our series on machine learning in healthcare. Through this series, we've been learning from our esteemed colleagues and researchers about challenges and opportunities about applying machine learning to our healthcare problems. So before I introduce our guest today, as an act of reconciliation, I would like to acknowledge that the land upon which McMaster is located is the traditional territories of the Mississauga and the Haudenosaunee nations, and within the lands protected by the Dish with One Spoon Wampum Agreement. And that wampum, which is a beaded belt, uses the symbolism of a dish to represent the territory and one spoon to represent that people are to share the resources of the land and only take what they need. And I share this acknowledgement as a sign of respect to Indigenous peoples in their enduring connection with the traditional territories and with its histories. I invite all of our attendees to acknowledge the land from which you join us today in the chat if you would like. So our speaker today, coming to us from the evening times in the UK, is Dr. Maqbool Hussain from the University of Derby, where he's a senior lecturer. And his research focus is on computerized decision support system and interoperability, a topic that is no doubt top of mind for many of our Hamilton Health Sciences colleagues who recently went live with Epic electronic health record about 2-3 weeks ago. So I'm sure they are learning all about the pros and the cons and the benefits and some of the challenges with computerized decision support systems. He is also currently working on representation of healthcare knowledge using knowledge graphs and is going to share more about that with us today. So thank you, Dr. Hussain, for joining us.
Okay, thank you for the introduction. Good afternoon, everyone. I would like to discuss today on the medical knowledge graph, which is the topic I have just given title, a revolutionary knowledge representation dimension in medical domain. I would like to share my experiences. First of all, I would like to just introduce somehow what knowledge graph is and how we can use it in medical domain. Then, of course, I have some case studies that I have been working with two different hospitals, one in the Haniport Hospital, Michigan, and one in South Korea. I will just discuss those two use cases, and of course there are a couple of other things I have to finalize. So the agenda will be, we will have to introduce the key concepts, the motivation of the knowledge graph, and one of the main thing is how knowledge graph should be constructed, the key approaches, and what we have used. Because there are some common processes and steps exist, but for each domain and with each requirements, some changes are made for customization of your knowledge graph that support your requirements, that support your healthcare domain that you are targeting. So in this particular session, I will introduce one case study from the brain aneurysm, and another case study I will be going to introduce from bioinformatics domain with cancer as a main disease. And then I will just highlight some briefly introduce that nowadays emerging trends of emerging technologies like digital twins in healthcare, how the knowledge graph can play is playing a role over there. So the thing we must have to keep in mind that we have sheer amount of data available in healthcare. And the key thing that the data available with us is coming with different formats. Those data sources have different layers. For example, we have a variety of data in primary, secondary, social care, etc. At the same time, the data can be comes with different characteristics. For example, we have sort of clinical data, which is available somehow in structure, unstructured, and even online evidence-based data. Somehow we can categorize that one as a knowledge. And the other sort of data that is available, which is nowadays is the focal point for the research and involvement in the healthcare, is the genomic data, which of course is bringing the domain towards the from personalized medicine to precision medicines. So all these different heterogeneous data sources that we have, or which are available within the healthcare organization or across healthcare organizations, are coming in different varieties. Furthermore, if we can see the IoT-based healthcare devices, they are providing bunch of streamlined data. So all these data are actually coming in different formats. And of course, in order to provide end-to-end services, we must have a unified model of representation of these data sources. At the same time, the processes that we have for the in the healthcare workflows, so that unified models will allow us to provide standard accesses to the data, as well as unifying the workflows, which will streamline the analysis, ultimately improving the clinical workflows. And also we have to enrich different data by including different vocabularies and different other meta information that will comes with different research outcomes, etc. So that unified model that if we are looking nowadays is can be provided by the knowledge graph. So based on this unified model, one can be able to analyze the data which is coming in a variety of formats, and at the same time, it will allow us to share this data across different organizations for the different needs. So that unified model that I have just used the term is the knowledge graph. So just let introduce the knowledge graph, or what knowledge graph is very simple concept of knowledge graph. We have in layman terms nodes and connections, and the nodes we are just thinking about are normally entities, and connecting two nodes or correlations. Just for example, World Wide Web is a huge network of concepts which is associated to each other. So here I have just put the first example of non-clinical for the Tim Berners-Lee, who invented the World Wide Web. So if we would like to represent Tim Berners-Lee and associated resources with Tim Berners-Lee, so simple thing, we can just draw a connection between the concept which is associated with the Tim Berners-Lee. For example, Tim Berners-Lee is the son of Conway Berners-Lee, and he is the winner of the Turing Award, and he has invented the World Wide Web. Similarly, you can see all the concepts in the knowledge graph domain is actually connected to each other with inferenceable or inferenceable and typed sometime relations. You can just connect the nodes, and then you can reach out any of the information through all these connections. So a simple concept that we have for the knowledge graph. Looking simple, but it's very strong in terms of it has a lot of advantages of we can infer different information from existing information from existing entities and relations, and we can say that we can evolve the graph through the self-inferencing mechanism and many other advantages it have because of simplicity and well managing for the storage. So just to look for the clinical knowledge, you can see here, this is one of the initiative where they have taken into consideration different databases, actually the clinical information as well as different proteomic informations have been represented through these connections, and those connections have been established to formulate a unified model which is accessible for the new experiments, and they can take advantage of this one. So for example, you can see here GWAS study is one of the genomic studies which is associated with publications, and the publication is having targeting some functional region and tissues and then clinical pathways. Similarly, certain disease have all these information have been associated through simple connections and relationships. And these simple connections and relationship of nodes actually provide a lot of information that is used for further analysis, and different analytics can be derived from existing resources. In biomedical work, for example, for the experimental work, this knowledge graph can provide a very very easy formulation to draw a hypothesis. For example, establishing a new experiment based on that hypothesis, which is actually available in a single unified model, and they can infer. So if we can see this knowledge graph that has been created, which is including around 35 node types, and almost you can see the figure, nodes and relationships, a lot of relationships here, and different type of relationships it exists. The key thing is this knowledge graph has the association of clinical characteristics, which may sometimes be called phenotype with the genotypes, and the bioinformatician can take advantage of this resource to utilize in their new experiment. So the key concept in the knowledge graph is, first of all, how you can construct the knowledge graph. So it is important to know what sort of mechanism, methods, types of knowledge bases, and level of knowledge extraction is required. So if we can start from the level of knowledge extraction, what we will have two types of things to consider whenever we are going to construct a knowledge graph. First of all, we must have to look into the problem domain and understand which are the entities and which are the relations in that particular domain. You must have to identify. And in entity level identifications, you have named entity recognitions, name entity disambiguations, for example, and name entity linking. These are some key concepts you must have to understand, and then you can derive which concept should be entity and which entity, which concept should be a relation. And whenever you decide a relations, then you must have to identify whether the scope of that relation is global or local, so that you can give a proper namespace for that one, and that can be used in the context of local or global context. Then once you have these things in consideration, another thing you must have to consider is the which type of knowledge base you are taking into account. Actually, there are three main categories. One is you have schema-based. In schema-based knowledge graph, you have to define a proper types of each entity and relations. So you can see this is a strong type-based knowledge graph, which is actually making the knowledge graph more stable, but a more closer one. And again, in schema-based type, you have two approaches. Either you can construct knowledge graph from bottom-up approach, or top-down. Bottom-up means you have already existing data, and then you have to create a graph, and then schema is derived after you have identifies entity and relationship. Then you can define types for that one. In top-down, you have already predefined structured data, for example. Then you will need to define first schema, and then you create the knowledge graph instances. Schema-free is just like is open, and you have to add nodes and relationships without any concerning of the types. So this type of knowledge graph is mostly available in open area, and those knowledge graphs are not targeting a simple domain. So far as the schema-based knowledge graphs are sometimes considered as domain specific. For example, if we are going to create knowledge graph for the healthcare, so we normally have to use the schema based to make that domain specific. And the third one is the combination of the two. You have semi structure. You have some nodes and relationships, entities which will be typed, and some of them will be not typed. You can make them free without any consideration of the typing. So that is considered as a hybrid approach. So we'll discuss somehow how hybrid approach is actually working. We have one good example with us in case study. And the construction methods, how you can construct the knowledge graph, you can use the rule-based approach to identify, construct the knowledge entities relationship, or you can use semi-unsupervised learning, neural networks, or all others types of machine learning or other algorithms you can apply based on your data that you have in hand, and you can apply and you can construct the graph. So the common processes normally identified, there is, of course, specific steps identified by each individual, by each researchers based on the domain requirements. However, these are the some common steps that you will have to take into account while constructing the knowledge graph. So the first thing is you must have to identify your data nature, which type of data you are just targeting. Like, for example, your data is structure, semi-structure, or somehow having more semantics, more context. For example, you have clinical nodes, you have EHR or something. So based on that one, you then divide, you have to decide that my data is having, for example, clear representation, or it is purely structure following some standard representation scheme. So while doing this one, if it has clear domain ontology or structured data, then what you will have to do to redefine the clear ontology. For example, if you are using the electronic health record, which is based on relational database, which is using relational database. So what you will have to do is you can construct a schema for the knowledge graph at first, and by transforming the relational schema into the knowledge graph schema. And then you will then start the knowledge graph concept extraction, like entities, relationships, and different attributes based on the available data. If you have clinical notes or other things, of course, then you will have no clue of the actual structure. Then you will first have to extract the entities based on the different methods you can apply. For example, NLP methods, etc. And then you can later on, if you want to schema-based knowledge graph, you can construct schema out of that one. Next thing is you have to process the knowledge. So once you create the entities, relationships, and attributes, then you have to integrate to all those artifacts that you have identified, and you will have to comply your instances to the ontology that you have created. For example, you have to check for the typing. All the types will be checked, and then you can complete the knowledge graph. So once you conceptual representation is completed, then you have to store the knowledge graph, and you can visualize, and you can then use that knowledge graph whatsoever you want. And the final step is because with the time, your concepts will be emerging, your new things will coming in, so you will have also to evolve your knowledge graph. And at the same time, if your knowledge graph is self-inferenceable, some new knowledge will be growing over that one, so you have to evaluate your knowledge graph, and then you have to maintain that knowledge graph. So in this particular session, what we will not cover up all the things, rather than the focus will be how we can construct a knowledge graph with the first 3 or 4 steps. And the maintenance, we are not talking about how to maintain or how to evolve, just to give you an overview of the first 3-4 steps. Now, the thing why I came to the knowledge graph area, my main area is the clinical decision support system. So what key framework I have developed for the clinical decision support system is that we are actually combining the knowledge from 2 resources. First one is we are applying the machine learning approaches to create a knowledge, and at the same time, I am collaborating with the domain experts in different disease domains while using their domain heuristics as well as the clinical guidelines they are applying, combining the knowledge model from both together, and a hybrid knowledge model is used for the decision support system. And at the same time, what we are doing, we have developed different knowledge acquisition toolset, like for example, authoring tool, and we have also provided the validation, even formal verification for the knowledge when we have combined. And finally, the knowledge we have created for one of the hospital was converted into shareable knowledge format, which is called HL7 Arden Syntax. So the knowledge representation that we have developed, this one, we actually, if we can summarize this one in a single slide, we are taking the clinical guidelines and convert into a clinical knowledge model. And then we are using the data-driven approaches using machine learning algorithms, normally the white box approaches, decision trees, for example, and convert into the somehow prediction model. And then we are combining those together into a hybrid knowledge model, which we call the refined knowledge. So this one is then used in the clinical decision support. So to do this one, we have these are the some key knowledge features we are getting from this process model, and we have defined the overall process into 3 phases. In phase 1, we are creating the clinical knowledge model. In phase 2, we are doing 2 main activities, creating prediction model and then combining into refined clinical knowledge model. And then in the 3rd phase, for the executable knowledge, we convert this refined knowledge model into HL7 Arden syntax. So just to give you a brief overview of the outcomes of each phase, I have this one. For example, if you can look around this model, what we have created with the domain expert in the domain of head and neck cancer, they have used their heuristics, as well as we have consulted different clinical guidelines, like, for example, NCCN guidelines. So they have created this this type of the clinical knowledge model, which is giving somehow how different treatment plan can be arranged for the different patients based on the, for example, the characteristic of, for example, pathological staging and different other risk factors. So this process is actually involves to define intervention, and as well as selecting the clinical guidelines, and of course then the domain expert's own heuristics. So it somehow is a rigorous inspection process, and this process is used to create this type of knowledge model. And then we have the medical data. For example, for the head and neck cancer, we have around 5,000 patient samples data we have used in this particular case. So this prediction model was actually created out of that, based on the different algorithms. So we have used different algorithms, like, for example, decision tree algorithm. These are different performance parameters, and based on the high ranking. And this decision prediction model has been created for the head and neck cancer treatment plan. And in 3rd phase, what we have a validation framework which combines the 2 model that we have seen, the clinical knowledge model and prediction knowledge model, and we actually get the refined clinical knowledge model. So just for simplicity, this one I have shown you one example of the same one. The intention of this slide is just I am just giving overview why we are moving to the knowledge graph. So you can see we have a final knowledge model for our clinical decision interventions. We are using this one, and this model we are then converting into executable format using HL7 Arden syntax. And this is used for the intervention in the head and neck cancer. Similarly, we have another case study. This one we have used with the Seoul National University Hospital for the thyroid nodule recommendations interventions, where we have just used the domain expert heuristics through the mind map, and then we converted into this model, which we call iterative decision tree. And this iterative decision trees we have converted into our production rules, and those production rules becomes part of the knowledge base to provide different interventions. Now, the thing is, at this step, we were having only the knowledge representation, and we were always need to convert this representation into production rule or any other format to be executed. And another key disadvantage of this one is, although it has all the rules and recommendations, but this model is not active in terms of it has no accessibility to the data source. So ultimately, what we were relying always on the other transformations, for example, other syntax or other things. So keeping this thing, to avoid this thing, we have started trying to use the knowledge graph. And the first case study that I have applied with the brain aneurysm, where I have worked with the University of Auckland, Michigan, which was working for the brain aneurysm. So in brain aneurysm, what we were supposed to establish a knowledge graph from clinical notes initially, and then that should be used to predict a rupture risk for based on different features. So what we have proposed in this particular design, we have targeted three main things. First of all, we have identified the concept and semantic relationships from the clinical notes. And another aspect that we have targeted, we have defined the swirl rules. The swirl rules were to provide the rupture risk as well as to calculate some statistical relationships. So keeping these three things in mind, all the informations were actually captured through knowledge graph. And during the knowledge acquisition process, for example, for the clinical notes, one of the team dedicated for the NLP process, they have already established that one, and we have just used the work which was initially developed based on the text processing, and they have already identified different concepts. And then what we have done, we defined the association rule mining based on the existing data and some other ensemble based running and production rule induction. We have developed association rules based on the extracted data, and then we make that as a part of the knowledge graph. And the statistical relationship that we have calculated different attributes, we have categorized into different orders, first order, second order, for example, mean of rupture risk factor, similarly, what is the odd ratio, etc. There are many information that have been categorized, and then we make that one as a part of the knowledge graph. So just take an example in here. For example, this one is a partial piece of clinical note, 55 years old, Caucasian male with no history of cerebrovascular disease, presented, identified with intracorneal berry aneurysm. So if we can convert this one, what the framework we have identified to know the actual entities and relationship, and then we have converted that one into this particular knowledge graph representation. So for example, if you can see here, in this particular case, we have disease, which is cardiovascular system disease. Of course, this cardiovascular is not here, but we have identified this one from another taxonomy. And then based on, this is, for example, vascular disease taxonomy, we have created this formulation, and then we combine both together this piece of the knowledge graph to convert this one into a complete knowledge graph, which represent, for example, which can interpret all this semantic that we have covered over here. So keeping this one, this is just, for example, if we would like to incorporate two clinical notes, fraction of two clinical notes, you can see here, we have made a clinical note as a concept, and then we have associated this with the aneurysm entity, and then aneurysm entity. For example, in this particular case, the aneurysm occur at MCA or MCA port, middle cerebral artery, and this one is then connected to the body port, which is coming from the vascular system, and we have just embedded the concept from different terminologies. So a complete port of this one can be used over here. Similarly, if you can see here, has a probability RCI 778. This is one of the key innovation in this approach, that we have associated the statistical attributes and relationship and entities. RCI is a risk calculation score that we have identified for the aneurysm. And similarly, if you can see, there will be rupture frequency. This is 23. So for example, for Caucasian, 23 persons are currently in the knowledge graph. So all these features are statistical, and some of them are the specific to the nodes and conceptual. So 3 levels of the attributes we have identified in this approach. And this is the overall framework that we have created. So I will just not going into details, just to show you the key processes that is related to the knowledge graph is here. So once we, for example, once we generate the, we extract the entity and relation and then statistical relationship, then we convert that one into a knowledge graph. But the knowledge graph at this stage is just considering the data and entity. What we have just new thing in this particular case is we are making hybrid knowledge generations, which means that the knowledge graph will have not only the entity relation and other stuff, but also having associated with the different machine learning models that is actually coming from, for example, decision tree we have used, and some ensemble models and other algorithms we have tried over it, which will actually work on the existing knowledge graph. And then at the same time, we have also take advantage of the swirl rules, which is coming from the ontology perspective. So those rules have also been incorporated, and overall a knowledge graph is having, you can say that the recommendation for the rupture risk was coming with different perspective. First, the RCI, the risk calculation index score, and then there are some swirl rules and many other things, many other models that we have used to predict the rupture risk for a particular patient. These are some key algorithms for the text processing. Is a relationship extraction, for example, concept extraction, and risk vector relation extractions that we have implemented for the knowledge graph construction. And these are the some key results that we have for the concept extraction. Similarly, taxonomy relationship extraction. And these are the some evaluations of the ensemble model that we have used on our data. And these are the production rule evaluation that we have created for the which is based on the data we have created, and we converted into association rules, and then inducted from those association rules set of production rules. And we have also incorporated that is a part of the knowledge model. So this was the thing that we have done, but what we have not done, and now we are just focusing on that one. We actually converted. Now this work is in progress, and somehow we have some results out of it. What we have converted, that we have consume the local EHR data, which is structure. And at the same time, we have collected the global evidence from online published resources, converted this one into a mind map, and then the domain expert actually converted into a refined knowledge model. And then we incorporated this one into our what we can say the knowledge base. So I will show you some example in here. For example, if I can run that, I will show you the outcomes of this framework that we have. So, right. So is this screen is available, the PDF?
No, we're still seeing the PowerPoint.
See, right. Okay, let me share this one.
Yeah.
Right.
Yes.
So if you can see this one, this is the ACOM. ACOM is one of the artery in the brain. So what we have generated a knowledge from the structure data based on these key features. So our representations actually generate these sort of representation. So if you can see, if the patient is adult with hypertension, yes, multiple aneurysm, no, and the side of the aneurysm is left. So the rupture risk is 34.5%. Now, if, for example, if we add another, if we have been known with the other information, for example, is white Caucasian, then the rupture risk is 19% increase, which is 41.0%. At the same time, for example, we have categorized the aneurysm into small, tiny, and some other factors. So other sizes, then it says that if you also know that the aneurysm size is small, which is around the standard size is 2 millimeter. So the rupture risk will be 44.5%. At the same time, if you can go this way, so if the aneurysm is small and the gender is female, then the rupture risk will be 46.7%. So this is one representation that we generated out of this one. Similarly, if you can see, the model which is generated other patterns too. So what we call this one as a what the doctor is sitting looking into patients, and they like in natural way what sort of information is available to the doctor. So they further predict what is actually happening to the disease. So in this particular case, what the rupture risk for that particular disease is in that particular area. So this is just take another example. If you can see, we adult with multiple aneurysm, no white Caucasian left. So 34%. If you can go this way, female 39.7%, similarly so on so forth. So you can see this, our model have created different 88 patterns you can see, and these patterns can be used for your decision making. More particularly, we are targeting this one for the chat bot for recommending the rupture risk. So now the problem with this one, as you can see, we have a lot of trees in here. So let me go back to my right. So the screen is now available, the presentation, right?
Yes, it is.
Okay, so those different, if you can see different features, different risks, what we have calculated is problematic. So what now we are targeting that we have to convert that one into a probabilistic inferenceable knowledge graph. Of course, this one is this research is now going on. What we are targeting that we have to achieve that incremental inferencing rupture risk calculation, how we can deal with that one is now going on, and we are converting that model into the knowledge graph. So this is our next research, what we are now conducting, and this is our core model that we have already created, and that we are taking into account that we have to divide into 3 parts. And we are just targeting how from each part the knowledge can be fused together, and how can we validate, and how the rupture risk prediction can be calculated. Another key case study we have is the BioKG portal we have created from biomedical knowledge. So in this particular case, what we have done, there is a target gene, for example, STK3, we have targeted in the breast cancer in association with the clinical characteristics. For example, what sort of expression of the genes can be observed within the breast cancer patient, particularly the breast cancer subtype, for example, basal, luminal, and luminal A and luminal B types. So the standard workflow we have defined over here, if you can see, we have used the bioinformatic pipeline process for this analysis, and I will just give you some quick overview that how we have identified the STK3 association with the clinical characteristics, and then we have also identified that in association with the STK3 gene, in association with the different cancer subtypes, and what all other genes can be ranked according to the expression level that we can observe. So the first thing we have been observed that STK3 has a different association at different cancer type. At the same time, we have also ranked 10 other genes which are having a high association with the, like they are the potential biomarkers in the breast cancer. And the methodology, I'm not giving in details, it's huge things, but just to highlight that one of the outcomes of this one, if you can see here, these are the different things that we have calculated, for example, enrichment score, and then gene expression level, and in different data for each gene, and then particularly with each clinical pathways, what is the maximum gene expression of each gene expression in association with the clinical characteristic. And finally, we have certain model to rank all those genes. So we have identified 10 different genes identified which are potential biomarkers in association with the STK3 in different cancer subtypes. At the same time, this is another result that we calculated. For example, if the patient is basal, what is the, for example, probability that GGH is another gene that we have ranked, how is its expression will be looking like, what is the probability, and in association to the STK3, how much, whether the higher expression of one gene is also resulting the higher expression in certain cancer or not. So these different results have been calculated and are used in decision of the biomarker identification in the breast cancer. And of course, once we calculated all these aspects from the genes, we have gene sequence data and we have clinical data. All these informations when we were targeting, so we have also calculated these sort of other meta information, meta results outcome. So now the thing is, how can we incorporate this one into a certain unified model so that it can be used for further future uses? So for that purpose, we have also started parallelly a BioKG portal project. The target of this one is that we have to use the knowledge graph approach to convert the data as well as the outcome somehow into knowledge graph, and which should be used in future for example, experimental work, or it can be used by other researchers. So just to highlight, we have just done a prototype model for this one. We have assigned 1 master student and 2 undergraduate students to implement and just develop a prototype model for this one. So what actually we have done, for example, the core differential analysis is called gene set enrichment analysis we have done, and we have used Grecan. Now it's called vertical knowledge graph to create the BioKG portal, and then we demonstrated a prototype model. How can, for example, gene set enrichment analysis from this model can be done, and how different other information can be extracted. So for the gene set enrichment analysis, we have implemented this model through Python, and then we converted the clinical and genomic data into the knowledge graph. So for example, you can see this is one of the schema from clinical clinical cancer data we have created. This sample is taken from for the thyroid cancer. So all this information is coming because the data provided at the TCGA portal and the BioKG portal, they are structured data. So we can see we have developed first of all the schema out of that one. Just to look around here, for example, we have cancer, which is associated with the tumor, for example, and these are the different attributes that we have derived from that particular data. And at the same time, we have also created a model for the genomic data. So then we have combined that one together and implemented in the Grecan. So this is the Grecan. Grecan is, there are 2 main tools nowadays used. One is Neo4j and one is Grecan, which is then has been renamed as vertical. The difference between 2 tools is what I have told you, that, for example, you can create schema-free or schema-based or in principle knowledge graph. Grecan is targeting, it allows you to create a knowledge graph which is having predefined type schema, and it can be inferenceable. So far as Neo4j is more focusing on free schema-based knowledge graph, you can create just free knowledge graphs. Of course, they have all those support, but this Grecan or vertical is more stronger if you want strong inferencing and strong typed knowledge graph. So what we have used in here, the vertical engine to store all those information, and then we have developed these tools to produce different analysis out of that one. And if you can see, this one is some of the results that we have generated while using behind the scene the knowledge drop that we have created. And we have also created, for example, this is one example of the heat map that we have generated based on the genomic and the clinical data. and these are other information that we have extracted. So this was sort of preliminary prototype model that we have created. Of course, genomic data and the clinical data is not only the source you can use for the bioinformatic analysis. There are proteomic, there is a protein-to-protein analysis. Many different aspects should be covered. So we are also extending this, this research further to cover up the protein-protein analysis and many other databases that are openly available. So these were the two case studies that we have. And finally, just to summarize, digital twins, we know that digital twins are nowadays very in different domains, particularly healthcare is also one of the target domain. So where the aim of the digital twin is to represent the real world object, simulate that one, and make that one machine readable, so that we can avoid any discrepancies beforehand. So constructing digital twins mainly require that you have different amount, different type of data, and then you have different entities in real world you can model, and then you have different information which will be available across different systems and you have to use. So mainly the 5 dimensions are actually for the digital twin, like physical entity, you must have virtual entity, and then you have services which are based on the central data model, which have connection together. So the information will be split across different systems and different types, and the amount of data will be available. If we can map this one into healthcare model, so you can see, for example, you can see operation theater, and then you have eye doctor, and you can provide services. The information can come from different data sources with different types of data, and then you can simulate the physical environment in a virtual way. And now the thing is where knowledge graph can be used here. So you can see the data model is the key, and there are the simulation, and of course the physical entity can be also represented in the knowledge graph. So just to summarize over here, knowledge graph is considered one of the strong unified knowledge representation scheme that can cover up diverse data from clinical to genomic data, from unstructured to structured data, and the scope of the knowledge graph is not only to represent the data, but it can also cover up the configuration processes and virtual entities like what we have nowadays in digital twins. And freedom of knowledge representation, you can have typed schema, non-schema based, lightweight knowledge graphs, whatsoever you want, you can create out of it and you can use out of it. So this is all from my side. If you have any question, I will be happy to answer.
Great, thank you so much. That was a lot of information, and really interesting the way the various elements of data are coming together and being represented and then implemented. I'm going to open it up to see if there's anybody who's joined us who has any questions. Just feel free to unmute your mic, or if you prefer, you can also use the chat. I get one of my questions, because we're always a bit more on the implementation side, and I'm wondering what kinds of barriers you're finding with integrating the knowledge representation.
Yeah, what we have observed, the main thing with the, for example, the vertical, the Grecan we have used initially, it was a bit hard to, for example, in case of the genomic and clinical data, clinical genomic data are available in sort of, you can structure file format, CSV format. So whenever you define the schema, So what the mapping of the single file into multiple entities is different, and what actually happens in vertical case, we were facing some problem in converging a single file into multiple entities, and we have done a lot of custom work which we have put down to the vertical team, that, for example, it should be facilitated, and of course they are now providing some intermediary to facilitate those things. So this was one key aspect. Another one is, as you know, genomic data, for example, for the breast cancer, it was around 60,000 genes we have to look around, and when it will be growing, so of course some scalability issue will comes in, and also there will be some need of high performance so that it can be processed with some reasonable time. So these two issues we have observed, and of course this was a prototype model, so we have not provided a complete solution for the performance issue, for example. That was, but the one which was integrating from a single to multi relations, multi entities, that we have resolved, and we have defined our custom code for that one. Yes.
Thank you. And is the intent then that because we're constantly generating new evidence and new data, that is integrated continuously?
Sorry, can you just repeat?
Yeah, because I think one of the elements was that it needs to be kept up to date. So I'm just wondering, does the data just continuously flow, or would that?
Yeah, the thing is, for example, once if your data is already, the structure is already defined, so of course you have schema for that one. For example, I am considering you are creating the schema-based knowledge graph. So then you will be not need to do the things whatever you have the integration application. So that will work fine with that one. Up until if you define some new concept, then of course you have to evolve your schema, and then you will have also to incorporate that one into your API that is actually importing the data. Yes.
All right, thank you. Well, I see that we're a few minutes past the hour, and there don't seem to be any other questions. I would really like to thank you for your time and for sharing your knowledge with us. I think it was there's a lot of things that all of us will have learned. So thank you so much for joining us.
Welcome.
And thank you everybody else for attending. All right. Okay. Have a nice evening.
Yeah. Thank you.
Bye-bye. Bye.
Bye-bye.